Welcome to the deep dive. Today, we are taking one of the most fundamental observations you can make about the night sky, how fast a star spins. And we're going to use it as, well, almost like a forensic tool to unlock the secrets of how planets are born.
It's a great topic.
We're peeling back the layers on planetary cosmogony to understand why the slow, measured rotation of our own sun isn't normal at all. In fact, it's a profound piece of evidence that our solar system even exists.
It really is a classic scientific mystery, and it feels almost, deceptively simple on the surface. Our mission for you today is to understand the physics that dictates whether a star becomes this stellar speed demon rotating at hundreds of kilometers per second or a slow spinning star like our sun.
And that difference, as we're going to find out, hinges entirely on the distribution of something called angular momentum.
Exactly. It's this fundamental characteristic of any spinning system. And we'll see how the simple act of stellar rotation acts as this incredibly powerful clue to the presence or, the absence of planets.
Angular momentum. Okay, so that's the key concept you need to keep in mind. We're talking about a system's rotational inertia. And in an isolated system, like a star forming from a gas cloud, that momentum has to be conserved. It can't just disappear.
It has to go somewhere.
Right. So the core problem, as we'll explore, isn't really where the angular momentum comes from. The mystery is where the star put it as it condensed. But before we solve that, we have to look back at the surprisingly difficult history of just figuring out how fast these distant suns were turning in the first place.
Oh, absolutely.
Yeah.
I mean, determining the rotation rate of a star that's light years away requires some serious ingenuity. The story really begins way back in 1877 with an English astronomer,
Abney.
He came up with what was, at the time, a theoretically perfect solution, using the Doppler effect, but applying it to stellar spectroscopy.
Okay, let's unpack the physics of that for a second just to make sure we're all on the same page. When a star rotates, you're looking at its surface. One edge of that visible disk is, inevitably moving toward us, and the opposite edge is moving away. The edge moving toward us experiences a slight compression of its light waves. That's a blue shift.
And the edge moving away gets a stretching of its light waves, which we call a redshift.
Exactly. So if the star were just sitting there, perfectly stationary, its spectral lines, those unique chemical fingerprints in the light would appear as these incredibly sharp, narrow lines.
But because of the rotation, the light that we get from the star is a blend of all those slightly shifted positions. The light from the blue shifted side smears the line one way, the light from the red shifted side smears it the other way.
So the faster the star rotates, the wider that spectral line becomes. It's like blurring a perfectly focused image. The width of that blurred line is directly proportional to the star's equatorial rotation speed, at least along our line of sight.
Brilliant in theory, as you said, but just brutal in practice back then. The initial limitations in spectroscopic technology meant that resolving those subtle line widenings was incredibly difficult.
And there was a bigger problem, wasn't there?
A much bigger problem. Early astronomers quickly realized that rotation wasn't the only thing, or even the main thing, that made spectral lines wide.
Right. You've got these really complex atmospheric effects, things like thermal motion, just the heat of the gas, and internal turbulence within the star's upper layers.
And those effects naturally widen spectral lines, sometimes dramatically, especially for certain elements. This meant that for decades, trying to isolate the true rotational signature from all that atmospheric noise was like trying to hear a whisper during a thunderstorm.
And different chemical elements were affected differently by these pressures, which must have made calibration almost impossible.
It was a mess. You'd look at one element and get one reading, and another would give you something completely different. It took a long time to sort that out.
So the breakthrough that finally unlocked the ability to truly measure stellar spin didn't come until much later.
Not until 1928, through the collaborative efforts of an American astronomer, O.L. Struve, and a Soviet astronomer, G.A. Shane. Their work was pivotal. I mean, truly pivotal, because they successfully developed the mathematical and observational techniques to distinguish that rotational widening from all those other complex broadening mechanisms that had plagued astronomers for decades.
Okay, so to give you a really visceral sense of this discovery, let's use the specific stellar comparisons they analyzed. We can look at 3 hot stars where the spectra are characterized by these really intensive lines from hydrogen and helium, which are excellent indicators.
Okay, so our baseline star is a star called I Hercules. When Struve and Shane observed it, its spectral lines were incredibly narrow, super sharp.
So that told them its rotational speed was near zero, or I suppose its axis could have been pointed straight at us, right?
That's a possibility, yes.
Yep.
But statistically, it's a good indicator of slow rotation. Now let's consider the next one, Ursae Majoris. This star measured a moderate but substantial rotational speed of about 210 kilometers per second.
Okay, that's fast. Our sun is, what, 2 kilometers per second? So this is over 100 times faster.
Exactly. And if you look at the helium lines in its spectrum, they are noticeably wider, fuzzier compared to those on a Hercules. The rotational effect is clear as day.
But here's the complication, and this is where the genius of their work really shines through. If you look at the hydrogen line in Ursae Majoris, specifically one called Hu,
Right, the gamma line.
it looked almost identical to the Ho line in the first star, in our Hercules.
Which seems impossible.
It does. How can a star rotating at 210 kilometers per second not widen one of its most prominent spectral lines? That feels completely counterintuitive.
This is the crucial distinction they made. The Ho hydrogen line in these specific hot stellar atmospheres is already massively widened by non-rotational atmospheric causes, specifically high pressure and thermal motion in the stellar atmosphere.
So it's already blurry to begin with.
It's intrinsically so thick that an additional 210 kilometers per second of rotational widening just doesn't make a significant visual difference. The effect is completely dominated by the star's own internal atmospheric dynamics.
I see. So to actually see the spin, you have to find a star rotating so incredibly fast that the rotational widening overcomes all the other causes.
You got it. And that leads us to their third example, a star called HR 2142. Here, the rotation speed is extreme, a staggering 450 kilometers per second at the equator.
450, that's almost unfathomable.
At this immense velocity, the rotational effect just overwhelms everything else. All the spectral lines, including that notoriously robust Ho line, become dramatically broadened. They get washed out, and in some cases, they're barely even visible anymore.
And so that comparison tracking the point where rotational broadening finally eclipses the atmospheric broadening, that's what allowed them to establish a reliable method.
Exactly. And once that method was established and applied across, the stellar zoo, the data revealed this enormous disparity.
A huge range. The sun, our friendly neighborhood G-class star, rotates leisurely at about 2 kilometers per second at its equator. But the fastest star spin over 200 times faster than that.
And the rotation speed isn't arbitrary. It's systematically linked to the star's spectral class, which is really just a proxy for its mass and temperature. The massive hot stars, the O and B classes, they're the speed merchants. They routinely spin at hundreds of kilometers per second.
And as we move down that scale to the cooler, less massive stars, the G, K, and M dwarfs, the rotation rates just plummet.
They drop off until they become what our sources call practical non-rotators.
And this brings us to the central piece of evidence that really anchors our entire discussion today, the F5 mystery. Because it isn't a smooth, gradual drop-off in rotation speed, there is a sharp discontinuity.
It's just an abrupt, almost vertical cliff in the data. This drop-off occurs right around the spectral class F5, where a star's surface temperature is approximately 6,000 Kelvin.
Okay, so here's where it gets really fascinating for you. Stars that are earlier than F5, meaning they're hotter and more massive, almost universally exhibit rapid rotation. We're talking typically exceeding 100 kilometers per second.
But the stars that are later than F5, the cooler ones, including our G-class sun and then the subsequent K and M stars, they are the lethargic rotators. They're spinning at speeds so low that they were initially classified as non-rotators until highly sensitive spectroscopy finally confirmed their slow spin.
So the fundamental question becomes unavoidable. Why does stellar rotation change so suddenly at F5? This characteristic, linked to the star's foundational angular momentum, is discontinuous.
Well, everything else, luminosity, mass, surface temperature, all those things change smoothly as you progress along the main sequence.
Exactly. So an abrupt change like this demands an equally abrupt, powerful, and very specific physical mechanism that's happening either inside or around the star.
And we believe that mechanism is intimately linked to the formation of planets. To demonstrate why, we have to start with that crucial and kind of counterintuitive insight that comes from the law of angular momentum.
Let's run the thought experiment. Imagine you can magically rewind the solar system's history and merge all the planets, from Jupiter all the way down to the smallest asteroid, and just put them back into the sun.
The result is staggering. Today, the sun accounts for over 99.8% of the solar system's total mass. It's almost everything.
Right.
But it possesses only about 2% of the total angular momentum of the system. The planets, particularly the massive outer giants like Jupiter and Saturn, they hold the remaining vast majority, around 98%.
So if that 98% of rotational energy were suddenly transferred back to the sun, its total rotational moment would spike from 2% to 100%. The calculation is pretty clear. The sun's equatorial speed of 2 kilometers per second would increase by a factor of 50.
50 multiplied by 2 gives you exactly 100 kilometers per second. This is the calculated speed that our sun should be rotating at if it had condensed from its original gas cloud fragment while keeping all the system's angular momentum to itself.
And that speed, 100 kilometers per second, that's the normal rotation speed for every star that's hotter and more massive than F5. That can't be a coincidence.
It absolutely is not. This is the immediate and most vital conclusion you could draw. The slow rotation of the sun and all similar cool dwarf stars F55, and later that is the anomaly. They didn't start slow.
He started fast.
They started fast, matching those O and B stars, but they managed to shed that initial high angular momentum by transferring it to the surrounding matter. And that matter became a vast reservoir of rotational energy.
A planetary system.
A planetary system. So the working hypothesis is established. When you look at a cool, slowly spinning star, you are very likely looking at a star that possesses a surrounding planetary system that successfully absorbed the lion's share of the original angular momentum from its parent nebula.
Which immediately tells us that planetary formation isn't some kind of rarity. It's a necessary consequence of angular momentum conservation in standard gas clouds.
Now we have to delve into the physics of how this angular momentum transfer happens so efficiently for these cold stars, but then completely fails for the hot ones. We have to look at the primary theoretical mechanisms that have been proposed to sort of pump this rotational energy from the central core out to the surrounding disk.
Okay, so let's start with the first major cosmogonic hypothesis. It builds on some early ideas from Alf Venn, but it was extensively developed by the English astrophysicist Fred Hoyle in 1958. This is the magnetic braking hypothesis.
Right. And we have to first acknowledge the scale of the initial problem.
Yeah.
Stars form from these vast interstellar gas dust nebulae, often light years across. Because of their immense size, they possess truly enormous initial angular momentum.
And if all that AM were conserved during the necessary gravitational condensation?
The star would spin itself into oblivion. It would have to rotate near the speed of light, which is a physical impossibility.
So our sources confirm that the nebula must first lose at least 99% of its AM before the main star formation even begins. Hoyle proposed this initial leakage happens via the magnetic field lines that thread through the collapsing cloud and extend outward into the interstellar medium.
The collapsing material drags those field lines with it, transferring AM out to infinity. It's kind of like a magnetic parachute.
But there's a critical limitation to that.
A very critical one. This mechanism stops working once the cloud density gets too high, and calculations show that even after losing 99% of its AM, the remaining rotational moment would still result in a condensed protostar or rotating at several hundred kilometers per second.
Which perfectly explains the OMB class fast rotators.
It does. So if the slow rotators, the F5 and later stars, are to get down to 2 kilometers per second, they must lose that final substantial chunk of angular momentum after they've already condensed down to the size of a nascent solar system disk.
This is where Hoyle's specific mechanism for planetary formation comes in. As the protostar shrinks, its spin rate rockets up until the centrifugal force at its equator causes matter to separate,
Forming an equatorial gas disk. This is the classic Laplacian scheme of a flat, spinning disk around a central object.
Okay, so how does the star use magnetism to talk to that disk and slow itself down?
The forming protostar possesses a robust magnetic field. The field lines pass through both the star and the separated disk. Because the star is spinning rapidly, let's say at that 100 kilometers per second, it continually twists or winds up those magnetic field lines.
Like a rapidly spinning axle twisting a set of ropes attached to a much slower outer ring.
That's a perfect analogy.
Yeah.
And that twisting action must create incredible tension.
It does. The tension in those wound-up magnetic field lines acts as a powerful magnetic brake on the protostar, slowing its spin. Simultaneously, the magnetic connection, the field lines themselves, pumps energy and momentum outward, pushing the disk matter into a wider spiral orbit.
So the angular momentum is successfully transferred from the star's core out to the disk, where it's stored and eventually forms the planets.
This sounds like a perfect fit, especially for explaining that F5 jump. Why is this mechanism efficient only for the cold stars?
It all comes down to stellar plumbing, really. It comes down to something called the convective zone. For the magnetic braking to be efficient and sustained, the magnetic field lines can't just snap under the strain of being wound up. They need a deep, stable anchor point inside the star.
And what happens right around that F5 transition? What changes?
So for cooler stars from F5 onward, they have a specific temperature drop below the surface, right around that 6,000 Kelvin mark, where hydrogen, which was ionized at higher temperatures, suddenly becomes neutral.
And neutral hydrogen is highly opaque.
Extremely opaque. This abrupt change in opacity completely disrupts the energy flow. Since radiation can't easily pass through this opaque layer, the energy transfer mechanism shifts from radiation to mechanical transport. And this is what drives the massive turbulent upward and downward convective flows.
So the star develops this massive deep zone of churning, boiling gas just beneath its surface.
Exactly. And this deep, turbulent layer provides the robust anchor we were talking about. The magnetic field lines get glued to this powerful plasma turbulence. They are submerged deep, anchored by the sheer mechanical force of these gas flows.
And that deep anchoring allows the star to efficiently wind up the field lines for long periods, sustaining the AM transfer to the disk without the lines just snapping.
Exactly right. And the opposite happens for hot stars. Stars hotter than F5, like F0 and earlier, they remain fully ionized right down to their superficial layers. They don't develop this thick, deep convective envelope.
So no deep anchor.
No deep anchor. The magnetic lines can only briefly connect through the sparse surface layers and the outer corona. The winding mechanism quickly generates too much tension, the field lines snap, and the outer gas disk, the potential planetary material, is just shed rapidly into space before significant AM can be transferred and locked into orbits.
So the sharp F5 boundary is ultimately caused by the delicate physics of hydrogen ionization and opacity, which dictates the depth of the convective zone, a subtle yet absolutely fundamental physical threshold that enables the long-term magnetic coupling needed for planet formation.
It's an incredibly elegant theory, but we do have to acknowledge the challenges that are detailed in our sources. Hoyle's hypothesis has two main issues. First, the mechanism is difficult to reconcile with how the disk material, which is mostly hydrogen and helium, manages to be sorted out to leave behind the small, heavy element cores that form rocky terrestrial planets.
Right, where does all the gas go? And the second issue is the scale of the required magnetism. If these field lines are meant to act as a powerful brake on a system the size of a nascent solar system, they must be immense and incredibly strong.
Yes. The primary astrophysical contradiction is that Hoyle's mechanism requires a magnetic field strength for the early protosun that is far greater than what is considered realistic based on current stellar dynamo models.
Okay, so dynamo theory, which explains how stars generate magnetic fields through the motion of conductive plasma.
It suggests that a young star at this stage likely wouldn't have the sustained, uniform, and immensely powerful field necessary to perform this level of braking over the entire disk. This weakness led astronomers to seek alternative explanations for the slow spin.
Which brings us to the second core hypothesis, and this one challenges the assumption that slow rotation proves the existence of a planetary system at all. This idea was proposed in 1962 by the French astrophysicist Schatzmann.
Right. Schatzmann proposed a mechanism where stars could lose virtually all their rotational momentum using magnetic fields and mass loss, what we call the solar wind, without needing a massive planetary disk to absorb the momentum. He was looking for loss without planets.
Let's talk about the solar wind mechanism. This involves the continuous streams of charged particles, or plasma, that are ejected from the star's active magnetic regions, like sunspots.
Correct. These particles are excellent electrical conductors, which means their movement is tightly constrained by the magnetic field lines. As they're ejected from the star, they shoot outward along these lines.
And since the magnetic field lines are rooted deep inside the star and rotate rigidly with the star's surface, the ejected particle stream has to continuously increase its rotational moment as it moves outward.
This is the crucial point. The magnetic field acts like a gigantic, rigid lever arm extending far out into space. It forces the outflowing material, the stellar wind, to spin along with the star long after it has physically left the star's surface.
And this dramatically maximizes the angular momentum carried away by each particle. It's like a figure skater slowing her spin by extending her arms.
A perfect analogy, but on a cosmic scale. When the particle stream reaches a certain point, say 30 solar radii out, where the star's magnetic field weakens considerably, the stream breaks free.
And when it detaches, it just rips off a disproportionately large amount of the star's angular momentum.
Precisely. Schatzman calculated that for the Sun to lose almost all of its rotational AM down to the current 2 kilometers per second, it would only need to shed a tiny fraction of its mass, about 0.001% over billions of years.
And that's a very plausible mass loss rate. We observe it happening now.
We do. And this mechanism also provides a potential separate explanation for the F5 discontinuity. Stellar wind activity is directly tied to magnetic field generation, which is in turn driven by the turbulent gas motions in the convective zone.
So since stars later than F5 have that deep convective zone, they have sustained powerful magnetic activity and a persistent solar wind. They can use the stellar windbreak efficiently.
And hotter stars, lacking the deep convective zone, have a less sustained magnetic activity, a weaker stellar windbreak, and so they retain their high AM. It's an elegant, self-contained mechanism.
So Schatzman's work threw a massive wrench into the machine. It suggested that slow rotation might just be an evolutionary trait of cool stars, not a proof of planets.
It absolutely did. But here is the critical counterargument, and this is based on observational data that's been gathered since the 1960s. Schatzman's magnetic braking model relies on that slow, steady mass loss operating over billions of years.
Meaning stars should start out fast and only slow down over time as they age.
Right. But if we look at the youngest stars, the pre-main sequence stars we call T-Tauri stars, what do we see?
We see that the low-mass protostars are already rotating slowly.
They're already slow. They haven't had billions of years for the Schatzman mechanism to work its magic. This strongly suggests that a major, highly efficient AM loss event must occur much, much earlier in the star's life, right at the formation stage.
And that observational evidence significantly diminishes the role of Schatzman's mechanism as the sole explanation. It forces the focus back onto mechanisms that transfer or dissipate AM during the core formation process.
Which naturally leads us right back to the idea of a massive surrounding disk.
This shift in observational evidence brings us to the third and perhaps most cohesive approach, the unified hypothesis, which integrates star and planet formation into a single, seamless event. We're talking about the work championed by the American astronomer Cameron, a major figure in the modern solar nebula hypothesis.
Cameron views star and planet formation as intrinsically linked, beginning with the gravitational collapse of vast interstellar clouds. And modern astronomy has, fully confirmed this basic mechanism.
But as we noted earlier, those clouds don't just collapse on their own. They need a trigger. This brings us back to the brilliant earlier idea proposed by the Estonian astronomer Epic that external events initiate the collapse.
Specifically, supernova shockwaves. When a massive star near an otherwise stable gas cloud detonates, the shockwave acts as this immense cosmic hammer, compressing the gas and dust. This compression increases the local density, pushing the cloud fragment past the threshold required for gravitational collapse to take over.
And our review of the literature confirms that modern observations, including simulations, strongly support this supernova trigger mechanism.
Absolutely. And Cameron strengthens this with direct forensic evidence found right here in our solar system, the anomalous isotopic composition found in meteorites.
This is truly phenomenal cosmic detective work.
It really is. Analysis of primitive meteorites shows the presence of radioactive aluminum-26. The key here is its half-life. It's less than 1 million years.
So it decays very, very quickly.
Incredibly quickly on a cosmic timescale. The only way this short-lived isotope could be present in the initial material that formed the solar system is if a nearby supernova exploded, spewed that material into our nascent solar nebula, and triggered its collapse, all within 1 million years of the condensation beginning. That explosion was quite literally at the cradle of our system.
Wow, so the massive cloud fragment collapses, but because it possessed significant angular momentum, the standard non-rare amount, it can't just form one dense sphere.
It's forced to flatten out. It becomes a massive, rapidly rotating gas disk, dozens of astronomical units wide, the solar nebula.
And now comes Cameron's crucial theoretical analysis regarding the fate of the AM. He argued that viscosity within this gas disk is the key driver of instability.
And we should clarify what astronomical viscosity means here. You're not talking about thick syrup.
Right, good point. In this context, viscosity is driven by turbulence and friction within the gas itself. This turbulence allows different parts of the disk to interact and exchange angular momentum. As the disk material loses energy through these viscous processes, theoretical models show that this leads to instability.
And this results in the rapid condensation of several massive gaseous rings.
And this happens fast. We're talking about the rapid, unstable formation of several, likely 2 or 3 massive gaseous protoplanets before the central protosun has even finished its primary condensation phase.
These protoplanets are immense. Around Jupiter's mass, maybe even the size of an AU when they're newly formed. Their early formation is the perfect solution to the AEM problem because they naturally hoard the majority of the system's angular momentum immediately.
Leaving the central material that's destined for the sun relatively AM poor, which explains its eventual slow rotation.
Exactly. The problem is solved right at the beginning.
So what happens to these massive initial hot gas clumps?
Their evolution is detailed by Cameron. They begin to contract under their own gravity, and their central regions heat up dramatically, reaching temperatures between 3 and 4,000 Kelvin.
Hot enough to melt virtually all the solid elements contained within the core of the protoplanet.
Everything melts,
Hmm.
and continuous convection within the gas giant then thoroughly mixes all of this material.
But the inner solar system looks very different from the gas giant outer system. So how do we get our small, rocky planets?
In the inner solar system, the gravitational influence and the tidal forces exerted by the newly forming central star are intense. These tidal forces essentially stripped the vast gaseous envelopes of any inner protoplanets.
So it tears away the gas.
It tears away the gas and releases all the dense, melted solid fractions, the silicates, the metals, back into the surrounding equatorial plane.
And at a later stage, once the sun reached its final size and most of the remaining gas was either used by the star or dissipated into the interstellar medium, the remaining heavy, solid particles, the melted mixed debris, settled into a thin layer in that equatorial plane.
And this is the material that forms the terrestrial planets, Mercury, Venus, Earth, and Mars, along with the asteroid belt. They formed from this thin layer via gravitational instability, particle collision, and the progressive growth of small bodies, or planetesimals. We also owe credit here to the detailed theoretical work of V.S. Safronov, who modeled the timescale for this final assembly.
What kind of timeline did Safronov's work suggest for the assembly of a planet like Earth?
Safronov's calculation suggested that the gravitational accumulation and growth of planetesimals into the Earth's current size would take about 100 million years. That sounds long to us, but in astrophysical terms, that's incredibly fast.
It shows the efficiency of the solid particle collision and accretion process once that initial gas disk instability, Cameron's protoplanet phase, has sorted out the AM.
And Cameron's unified model offers a great explanation for a long-standing mystery. The chondrules. These are the millimeter-sized, glass-like inclusions found in meteorites. They clearly suggest that their material was previously molten.
Right.
The existence of these chondrules is naturally explained if their material passed through the superheated, convective interiors of those giant gaseous protoplanets proposed by Cameron. They were melted, solidified quickly as droplets, and then released when the envelopes were tidally stripped.
Or, alternatively, the melting could have occurred if they passed very close to the blazing hot vicinity of the newly forming, powerful central protosun.
Exactly. Either way, the model links the high-temperature history of the debris directly to the mechanics of star and planet formation.
Stepping back now, the simple initial observation of stellar spin rates has led us to a statistical certainty. Planetary systems must be extremely common across the galaxy.
Because the law of conservation of angular momentum is an immutable law of physics. As we concluded, a collapsing gas cloud possessing a normal amount of AM, and over 90% of them do, cannot possibly form a single, slow-rotating star like the Sun without some form of companion absorbing the momentum.
If a slow, non-planetary star were to form as an isolated object, it would require the original collapsing cloud to have had an AM hundreds of times less than normal. This would be an extreme astrophysical rarity, something like less than 10% of clouds.
The consequence for our understanding of the universe is profound. Almost every star like the Sun that appears to be single must actually be part of a multiple system. They're either paired with visible stellar companions, a binary or trinary system, or they're paired with invisible low-mass companions.
Planets or brown dwarfs. Multiplicity is the rule, not the exception.
That's right. And this drives the question we care most about. How common are Earth-type planets? We can confidently predict the abundance of systems capable of forming Jupiter-mass objects, but rocky planets are a far more subtle thing.
This requires statistical extrapolation referencing historical work like that done by App and Levy. Let's take the optimistic, but I think reasonable case. The Sun, a standard G-class star, is typical in its planet-forming capabilities. We might estimate that perhaps 10% of solar-type stars, and possibly K-class stars have managed to assemble Earth-type rocky planets within their habitable zones.
Now, 10% might sound small to you, but when you scale that up to the hundreds of billions of stars in the Milky Way galaxy, that leads to a staggering conclusion.
It really does.
Under this optimistic assumption, the total number of planetary systems potentially containing Earth-type rocky planets could easily be in the realm of 100 million systems within our galaxy alone.
And statistically speaking, if those numbers hold, the distance to the nearest planetary system containing an Earth-type world might be as close as 50 light-years. While these are purely preliminary estimates, they provide a powerful orientational framework for future searches.
And what's incredibly exciting is how new observational data continues to directly support the general solar nebula hypothesis and the high efficiency of early AM transfer mechanisms like Cameron's.
You're referring to the cosmic masers, those intense natural microwave sources.
Exactly. Astronomers have been accumulating data on hydroxyl and especially water masers in space. These masers are physical manifestations of specific conditions in gas clouds, and when you model them, the source of their intense emission consistently points toward a massive, turbulent gas disk.
A gas disk highly reminiscent of Cameron's solar nebula right at the point of star formation.
Absolutely. The pioneering work of Soviet scientists V. S. Strelnitsky and R. A. Sunyaev was crucial here, as they were among the first to successfully link the presence of these cosmic masers, especially those from water, to the active formation of protoplanets within those massive disks.
So this allows us to observe the key mechanism of AM transfer in action, confirming the prevalence of these planet-forming disks around young stars.
It does. It gives us a real-time window into the process.
So let's synthesize this idea of multiplicity one last time. We know companions are necessary, but what decides whether a gas cloud forms a binary star, where the AM is locked up in orbital motion, or a planetary system, where the AM is locked up in the spin and orbit of small planets?
It seems to come down to the dynamics of the initial collapse and the ability of the star to form that robust, sustained convective zone. Short-period binary systems likely formed when a single, very dense gas clump fragmented into two primary condensations. All the AM is focused on their shared, tight orbital motion.
Conversely, systems like ours, a slow-spinning star with planets, suggest that the collapse was centrally focused, and the resulting protostar developed the necessary internal structure, that F5 boundary condition, to efficiently pump that AM out to a wide, low-mass disk before fragmentation could occur into a second star.
In every configuration, AM conservation requires the formation of companions. The resulting stellar rotation rate, especially that abrupt, non-smooth drop we see at F5, is the most potent, visible, physical evidence that the star successfully transferred that required angular momentum to a surrounding disk, validating the foundational connection between slow spin and planet formation.
This has been an incredible deep dive. We started by looking at the simple spectral blurring of starlight and discovered this intimate connection between stellar rotation speed, internal stellar anatomy, magnetic field dynamics, and the necessary mechanics of planet formation.
The key realization for you to take away is that the sharp, non-smooth drop in rotational velocity at F5 is not some random feature of stellar evolution. It is a precise physical fingerprint. It marks the temperature threshold where a star develops a deep convective zone, the essential prerequisite for the star to efficiently interact with its forming disk.
So that F5 boundary is the line between systems that must form rapid rotators or binary stars.
And those that have the physical structure necessary to shed their momentum into a potentially life-bearing planetary system.
That is a staggering conclusion, and it leaves us with this final provocative thought for you to consider. Given that the fundamental law of angular momentum conservation seems to necessitate the formation of companions, be they stellar or planetary, we should perhaps stop asking if planetary systems are common, and instead ask, what subtle mechanism, what small variation in density or composition in the initial gas cloud determines whether a collapsing mass forms a fast-spinning binary star or a slow-spinning star with a family of planets?